So it's great to be here and meet you all today. What I want to talk about today is how do we go beyond the topic of digital twins? How do we understand more and enable intelligence with in a scalable way from digital twins? I will probably end with telling you a little bit more about me, so bear with me, and I would like to get straight into the topic. Um, I think that you probably spotted the word environmental there, and the reason we want to start having this conversation, the reason this conversation is critical right now is that we are seeing a lot more affectation from climate crisis at the level of the cities, and at the same time we know that the cities are in part responsible or are contributing to climate crisis. We also know, and this is a metric that has been decided and defined quite a lot, that 70% of us will live in cities by 2020. The trend is very stabilized, so the trend is quite clear now, and will get us to the 70% number in the upcoming decades. And at the same time, we are already experiencing a large number of unsafe buildings and unsafe places, with an estimation of 20% of us living in unsafe places. So how does your city measure up? How do buildings in the city work in terms of climate? Are they 80% of the buildings are currently going without climate assessments? 90% of the cities face climate risk, and at the same time we have about 45% of the cities that go without a climate adaptation plan. Not to mention that the level of operational quality of the ones that do have an adaptation plan is still something that needs to be addressed and to be checked. So I wanted to split the talk in three acts. The first of them is digital twin. And why do we talk about digital twins is because as we understand that cities need to adapt to climate change, we also need to understand how they can actually arrive there, right? In the past decades, there has been an increasing trend of understanding that collaboration is essential based on data availability and interdisciplinary expertise, sharing information and decision making with this interdisciplinary expertise are all crucial aspects. Collaboration definitely requires a shared awareness, both in terms of spatial, temporal, and relational characters, and the ability to understand that the decision of one part or a decision that is very focused on a very defined place is going to have an affectation and will have consequences that go much beyond it. Data availability has also been an increasing trend in the past decades, and we see how more and more cities can take advantage of a number of sensors, a number of devices that provide real-time information, real-time data, and more platforms available to host this data. But if this data is not forecasted and if accurate data is not measured, it cannot be considered. And then with the multiple disciplines, multiple platforms that host the data coming from city sensor, we also begin to face this expertise level and interdisciplinary level, where multiple players will require to access and interpret different sources of data in order to arrive to a common intelligence, to a common decision. So a combination of all of this together on a digital, on a virtual representation is what we currently call a digital twin. Of course, this has various varying layers of maturity, varying layers of data, and it is meant to be an expansive system that can continue to evolve over time with technology and with the nature of the need. So at the moment we have, as I was saying, various levels, but there are three types or three understandings that are commonly accepted that will enable us to understand where we place a digital twin on the scope of maturity. We have first a simple digital model. Typically, we refer to this as a very high fidelity copy or digital copy of the physical reality. And this by itself already enables and supports awareness of spatial and relational aspects in the city, enabling more of these decisions supported by an understanding of the effect of the focus decision. Then we have what is commonly considered a very developed digital twin, but is could be considered a digital shadow. So this is a connected copy of this digital model. It attaches information to the inner geographic system, so in a GIS system, is enabled to capture this temporal nature of the physical reality through IoT devices. This allows responsive kind of nature of decision making. It allows an interpretation of causality, right? Why certain things happen. But then what would be considered a complete and complex digital twin, a level 3 or beyond digital twin, is an actual operational model of the physical reality, adding on top of copy of the data and access to real-time data sources. It would require adding the availability of simulations and predictive nature of that is accessed via analytics and forecasting. This can be developed to support autonomous decisions or human-in-the-loop decision, and by all means, it supports optimization as a way to arrive to a decision. There are indeed scales in between, and what I wanted to understand here is that mostly current state of digital availability goes up to level 2, right? Up to a mature digital model, descriptive digital model, and some connectivity, some work in progress diagnostic connectivity supported with real-time ingestion of data, where we really need to go in order to be able to take advantage of this platform as a operational intelligence platform, is adding this predictive nature of through real-time simulations and through real-time scenario and recommendations, where AI will play an important role. So the next topic, the next chapter that we need to talk about in this case is the availability of real-time simulations. So talking about climate adaptation, we know that decisions need to be supported on data, and that climate simulations are absolutely critical in order to be able to predict the impact, but also to plan, as well as to adapt to existing or to adapt to climate change. However, as we showed in the early slides in the metrics, these climate simulations are rarely accessible. We identified a number of common barriers that are impeding this to be accessed in design and in planning, mainly time and processing. Computing availability is causing a lack of integration. They are also complex, requiring specialized expertise and specialized knowledge, both to set up, to run, and to interpret. That makes them often become expensive, and even when all of these three barriers are overcome, they often are on a separate proprietary platform, making them relatively inaccessible in the different aspects, in the different workflows that require them. So Infrared City exists to simplify climate simulations, to make them available and accessible beyond this technical barrier and integration barrier that exists, but also to bring environmental simulations to a temporal scale that is acceptable within the nature of planning and the optimization work that professionals do, meaning that we are working to develop a real-time simulation layer, a real-time simulation basis. So what you can see here is a estimation of the time that is required for a typical computational fluid dynamics simulation. So this is one of the more time-consuming simulations, but also one of the more expertise requiring simulations. So this would require, between pre-processing of the data, the simulation, and the post-processing of the results, can go anywhere between hours and multiple hours and days or even weeks, in which case Infrared City can shed basically all this time and bring you the AI prediction of the simulation result in under a second. Of course, with real-time simulation, with real-time kind of response, there is an amount of accuracy loss. However, it's important to evaluate this accuracy loss, considering also the cost of not running simulations, considering the cost of not understanding the impact of the decisions beyond what can be measured retroactively, right? So for this, of course, to enable this to happen, in Infrared City, we build, as I said, the simulation layer, the simulation basis to deliver simulation results on multiple planning options on multiple platforms. And we do this via using AI models, which we train with hundreds of thousands of simulations run according to the current acceptable simulation standards. We use data from multiple cities around the world, augmented with synthetic data, and this enables us to train machine learning models, deep learning models specifically, that can predict the outcome directly without having to go through the time-consuming computational process of the simulation. We look at wind, as I mentioned initially. We look at wind patterns in the city, solar availability, thermal comfort, as well as heat stress and heat island patterns, and we are adding more models as well to enable a very multi-layered approach, multi-layered understanding of the impact of planning decisions. And on top of this, we are delivering this real-time simulation capacity via an open integration approach. So we are currently providing a cloud app, a cloud solution that enables anyone to access a pre-built platform based on a very low level of a digital reality, or the digital reality of the world, but of course with a lot of interactive ability to plan or to define your own planning, to bring in more sophisticated models and so on, and with a lot of features that enable optioneering, enable interpretation of the design results, easy reporting and collaboration. At the same time, we also connect directly into BIM, CAD, and GIS software via plugins that enable you to have this more direct back and forth, so the more direct sending and receiving of information for simulations directly from your existing workflow in case of a design workflow. But what is essential for what we're talking about today is our connection via API, enabling us to feed directly into digital twin platforms and to set up simulations, to deliver the results, and to connect this intelligence layer that I'm going to also talk about in the near future. So then the third step brings us to the topic of conversational intelligence and why this matters. And I think it's important to understand that with digital twin maturity, so with more layers of data, with more layers of interoperability, more layers of analysis and decisions added onto a digital twin, this complexity can lock in different expertise, so can kind of, or rather lock out different expertise, meaning that this becomes a more technical interface that requires support and therefore a different translation, which is something that we believe needs to be addressed, and we need to still enable the interdisciplinary nature and communication on top of the digital twin, which brings us to the aspect of conversational intelligence. So essentially deploying AI agents onto the digital twin, giving them access to tools, giving them access to data, and enabling with this a conversation with the AI agent, going beyond the barriers of linguistics, going beyond the barriers of technical knowledge or expertise. We have already built the first version of this AI agents and have already deployed it onto our cloud-based platform in the aspect of the reporting, which is essentially providing agents with access to all the project data as well as external tools, and supported on a knowledge graph or a knowledge base of expert literature, climate action, climate policy, all sorts of academic documents that are able to, so that the agents are able to interpret the visible results and deliver in a text format, insights and recommendations. This is now further implemented with giving agents access to data sources and analysis curation so that they can use mini analysis tools and visualization tools with access to multiple data sources and go beyond different layers. And then enabling them with, as I was saying, tool use, as well as chain of thought prompts and supported on this RAG retrieval augmented generation infrastructure. This enables this conversational localized intelligence to be used on the digital twin, enabling users to simply ask a question or describe the nature of their request or objective in natural language, and enabling the AI, on the other hand, to access enough simulations, to access enough data, and to be able to test multiple scenarios in order to give an end result, right? To give not an end result, but rather a next step to the user. So in this case, informing the user that a particular area needs revision. And this is what we have just presented. We are beginning to bring all of this together, both the aspect of creation of a digital twin with AI requiring access to or using access to satellite data and existing data sources to generate this digital copy of the reality provided by Aves Reality. The platform supporting digital twin, as well as the conversational nature and GIS operations operated and supported by NVIDIA Omniverse, and Infrared City delivering real-time simulation and this AI intelligence layer. So I will just play the demo that we also presented this week in the Smart Cities Expo Barcelona. And this is understanding or starting to look at the city of San Francisco, for which the digital twin was already built. A amount of territorial data was already evaluated. Simulations were run in advance to understand the nature of climate crisis over the next decades. And then a number of areas were looked into in more detail with simulation, with real-time simulations running to enable planning scenarios, as well as looking particularly at heat mitigation via multiple design options. Again, looking at multiple design options on a different area of the city, all of these areas that were evaluated and selected based on the access to data. So you can see the different areas that were the focus points. And in this case of a new building, also running real-time wind speed simulation to get this interoperability, so allowing the users to look at any potential option or any modification in real time. Thank you. I am Oana Taut. I am the one of the co-founders and the CPO of Infrared City. I think by now I already explained what Infrared City does, but we are building a platform for climate resilience for the cities, based on and supported with AI-driven simulations as a base layer, and AI-driven climate intelligence um, uh, for also communication and collaboration. Thank you.